scientific studies of this muon capture and some insight to physics beyond standard model and how muon capture can contribute to this neutrinoless double beta decay experiment. And I will show you some photos of my experience enjoying the beam time throughout my work as a high energy physics experimentalist. Okay. All might know this is the standard model of physics. So physics background is you must have seen this at least once within your study. Okay, so here we have in standard model of physics we have 3 sections. So the first section is quarks. So quarks consists of 6 flavors, which is up, down, charm, strange, top, and bottom. So indicate by here. So they call quark as flavors, not type. Okay. So and this quark actually have 6 different colors, which is blue, green, and red, and along with their anti-colors. This anti-blue, anti-green, and anti-red. Okay. The second section is the leptons. So this is the section that we want to highlight most in today's sharing. So the first is electron and its neutrinos, muon and tauan with along of its corresponding neutrinos. And we have 5 forces of interaction. So contribute from the strong nuclear reaction, weak nuclear reaction, electromagnetic reaction, and also gravitational wave. Okay, so gluon is the forces of interaction for quarks, while W plus minus and Z boson is the forces of interaction for leptons. And we have this photon, which is the forces of interaction for electromagnetic interaction. Okay, so, and this is the recent discoveries of Higgs boson, which is awarded with a Nobel Prize in 2012 in physics. So this indicates that the forces of interaction that give mass to all elementary particles. So in your nuclear physics class or elementary particle class, you might learn that these neutrinos don't have any mass. Okay, but now for the existing of this boson, so there's some postulation that's saying that this neutrino have a mass, but the mass is very, very small. Okay, okay, we goes to some muon facts. Okay, so muon have been discovered in 1937, okay, by the cloud chamber experiment. Okay, it have mass of 105.6 MeV over C square. This is the relativistic mass, and also we have the average lifetime of muon is 2.2 microsecond, and it is a spin half particle, so which is same with electrons. Okay, there are actually several groups of muon capture experiment. So we class it into its energy, the energy of muon used in the experiment. So the one that you might need to know is that we have positive muon and also negative muon. Okay, so actually the positive muon is interact like heavy electron. Okay? So it surely used for the material science where we require some interaction in the surface region. Okay, so this ultra slow and low energy, which is less than 30 keV, is specialized for muon spin resonance, muon catalyzed fusion, muon G-2. So this G-2 experiment also have some new announcement for maybe into 2020 or 2021 earlier. So this is related to the quantum electrodynamic problem in the nuclei, and so others is the material science and etc. Okay, so but for our case, we concentrate on this medium energy part. So here we have some experiment for nuclear and particle physics related to the muon minus experiment, where we investigate the muonic X-ray elemental analysis these are neutrino nuclear responses, and some particle physics experiment. This is mu2e and mu23 electron. This is a syndrome experiment and also comet experiment and others. And if you are using a very high energy of muon, so you are able to investigate archaeology or anthropology, which is related to the historical discovery. Okay, you can go for try to Google the cosmic ray tomography or radiography analysis using muon. So this part is actually the more natural muon that can be observed using this cosmic ray. So actually cosmic ray is penetrating throughout our universe for around 4 times 10 to the power of 3. Now, even though you are sitting at your chair, you are passing by a very high energetic muon from cosmic ray. Okay. Okay. So what happened when the muon capture on nucleus? So actually, since the muon is very heavy particle, so it was around 200 times much massive than electron. So it actually can be captured by any nuclei. So, but the probability of capture is proportional to number of electron. So as you see in the figure on the right, so this is coming from the physics report. So it is saying that as the Z number increases, so actually the probability of muon capture on that particular nuclei is become bigger. Okay, so what happened when the muon have been captured by nuclei? So they have two main process, which is one, the muon will decay directly into electron by the average lifetime of 2.2 microsecond. So it is following this Feynman illustration, Feynman diagram. Okay, so we have muon decay into electron and its antineutrino, and also we have this muon neutrino. So this have exchange of W minus boson. Okay, or they can choose to cascade down to 1s atomic state. Okay, so for this case, we slightly change the Feynman diagram. So here, if you did not see any proton, so we indicate proton by UUD. So this is the constituent of quark inside proton. And also UDD is the constituent of quark in neutron. Okay, so by changing transformation from proton to neutron, so they will have the exchange of W plus minus boson. Again here, so actually it was about the same but slightly different for this cascade down. Okay. Okay, so let's go to first the muon decay section. Okay, so actually because muon decay is a semi-electronic decay, so it does not involve any hadrons. So you know what is hadron? Anyone knows? Okay, so actually hadrons is a particle that is made up of quark. Okay, we have two kinds of hadron. One is baryon and another one is meson. Okay, so any combination of quark is called hadron. Okay, so the lifetime of this muon actually very much depend on the average of muon plus and muon minus. But however, muon plus lifetime is mostly constant. It's about 2.197 nanosecond or 2.19 microsecond. Is the same with the average. But however, the lifetime of this negative muon is much more difficult because negative muon interact with nucleus. Okay, when it interact, then it will stop on the nucleus and we cannot see it anymore. Okay, so that is why the lifetime of this negative muon is correspond to which nuclei that we are using as target. Okay, so but please remember that muon does not transform into electron. It always decay, but it can transform into muon neutrino. So this is the quark mixing our lepton mixing product. Okay, so this is similar and happen to all other leptons such as electron or tau. And then this is the nature of this lepton family. Okay, so the cascade, muon cascade. Okay, so muon cascade commonly occur for the medium heavy nuclei. Okay, it have lower probability for very light nuclei. So because the muon cascade usually happen when the incident muon replacing the electron inside the atom. Okay, but for gas type, the electron position is not fixed, right? So so it depends very much on the chemical and physical environment of the nuclei as a target, and it often occur on the bound state of the product nuclei. So this actually the product of after muon capture on X atom with A and Z. So we have one proton missing and transforming to neutron. So we have Z minus 1 here. Okay, so when the muon is replacing the electron in the orbital level, so this is called Auger electron process. Okay, so this Auger electron process, so actually it depends. If gas, so electron cannot be replaced. But if solid case, so the muon can replace the electron in the atomic orbit so that it is deeply bound. Okay, and upon replacing the electron from the lower states, so it will cascade down until the 1s level here, the one which is very most nearer to the nuclei. Okay, so this will take within around 100 or 200 nanosecond. Okay, and the transition rate between one level to another level, it's give some value for the negative muon lifetime. Okay, so every time the muon is changing this transition, so it gives some value for the muon lifetime. So we call this as partial muon lifetime. Okay, and then after Auger electron emission, so we have this muonic X-ray emission. So this is when the electron trying to return to the most ground state and then X-rays. So practically, muonic X-ray emission process is similar to the common electronic X-rays, only that the energy is shifted around 2 to 5 keV, just very, very small. Okay, and usually if we are using target which have many the environment which is not clear. For example, we have target and then we have some plastic scintillator, some aluminium and frame, so on. So this will be very much confusing when you are trying to use it as a calibration standard. Okay, because the peak for muonic X-ray is very, very sharp and it comes in group. It comes in group. So there's some tip to recognize this muonic X-ray. So it is narrow and have pattern and it emits instantaneously with arrival of muon. So due to this last feature, so actually if we want to do some experiment related to muon capture, so we must first observe this muonic X-ray, then we can confirm that it was captured on the nuclei. Okay, this is the first indicator. So otherwise we cannot see in the experimental hall, is it captured or not captured? Okay, so that is very, very difficult. So to confirm, so we can observe this muonic X-ray first. And then this is some of the muonic X-ray spectrum that I obtained from our colleague website. This is muoxrays.jnr.ru. So this is the example of aluminium. So we have K series and also M series. So, okay, as you can see here, the M series have 1, 2, 3, 4 nearby peak, and the 3 and 4 peak is very, very close to each other, but this one is more farther and so on. The similar pattern go to K series, so this is much closer and then become separated. And same goes to this niobium and also K series of niobium. Okay, so usually if you see for aluminium, we have the K series at around 350 to 450 keV. But for niobium, which is much greater heavy nuclei, so we can observe the K series around 2500 to 3700. Okay, if you take lead, such as lead, or much greater, so you can observe this until 8 MeV. So the energy become greater as the nuclei become much heavier. Okay. Okay, and finally, the final process is the nuclear transformation process. So this actually related to the emission of the muon neutrino. Okay, since this muon neutrino is very fast, have the kinetic energy of around 100 MeV. Okay, so that is why neutrino is called as ghost particle. So it actually carries the large fraction of kinetic energy after this muon capture reaction. So here we does not only consider the formation of A Z minus 1, but A minus X, okay, some other nuclear isotope. But in our study, we just leave it this X value until 0 to 5. So this is because of calculation value, and actually comes from previous observation from 1970s until now. So actually most of the gamma rays coming from this radioisotope of the nuclear transformation is only until 5, about 5. So we just stick to our study that maybe 5 is the maximum. So later if we find some details about the other nuclei, maybe we will introduce later. Okay, and then this probability actually initiate the nuclear cascade inside the atom. So where there are some possibility of A minus 1, Z minus 1 radioisotope gamma rays with 1 neutron emission, or 2 neutron or 1 neutron proton, and so on. Okay, so actually for light nuclei, there are some probabilities of charged particle emission, such as neutron or alpha particle. But for medium heavy nuclei, so mostly neutron, mostly is about 85% onwards. Okay, so but for light nuclei, it's about 70 to 60% of neutron. Okay, okay. Now we go to much lighter scientific study related to muon. Okay, so the first one is related to the nuclear transformation. So actually this method is very useful for environmental, such as radioactive waste management, or to produce biomedical isotope for treatment of cancers and so on. And it's actually the complementary method of neutron irradiation and also photon irradiation. So if you see at the table at the right, so actually if we are using ferrum 54, so for muon capture reaction, we actually can produce 55 ferrum. We can see we can get this 52 mangan. But on the other hand, for photon irradiation, we can observe ferrum 53. And same goes to here. And our most common target that we wanted to observe is this technetium 99. So this is very important for medical research for cancer treatment. And this is a radioisotope of 65.9, and this photon will observe 98 technetium. So anyhow, if we wanted to know which kind of radioisotope that can be produced by this reaction or other reaction, so actually we can just estimate by writing the nuclear reaction of this product, and then we can estimate the lifetime, the half-life. If the half-life is measurable, so actually we can extract this kind of isotope during the reaction. Okay, so this is the difference between muon capture. So we can observe the isotope in different isomers, but for photon, which is the same isotope level. Okay. So this is some elemental analysis for historical tempo koban. So this is the Japanese pole coins. Okay, so when we irradiated by this muon, so actually we can observe there are some muonic X-rays from aurum, gold, argentum, silver. Okay, so this is some composition. So let's say if so, we can say that there are some composition of these two inside here, and then we can extract the percentage of analysis for tempo koban. So it has been published by this paper. Next is the radiographic imaging by cosmic ray. So this method was first introduced in 2003. So it was using this radiographic emission, and then we can see that at the peak area, so actually we have some very dense colored pictures, and for the broadened peak area, so we have some small crumble. And the different group, this is Kyoto University, if I'm not mistaken. So they are doing this cosmic ray particle studies with the Egypt Red Pyramid, and they can see that there are some, this is actually the experimental data. So the top one is the simulation with Monte Carlo simulation. So actually they wanted to investigate what is this region inside the pyramid. So actually they get the same data, and turn out it was the hidden chamber of this that contains some nuclear isotope inside this pyramid. So they finally obtained this value. Okay. So let's move to the physics beyond standard model. So the contribution to this neutrinoless double beta decay. Okay, so the first, what is neutrinoless double beta decay? So actually this is one indication where have you learned about Dirac neutrino or Majorana neutrino? Okay, so the common neutrino that I introduced you before is called Dirac neutrino. Okay, for Majorana neutrino, so actually it have similar mass and energy for neutrino and antineutrino. Okay, so heard of Majorana. Okay, so actually this neutrinoless double beta decay wanted to prove the existence of this Majorana neutrino. Okay, so actually most nuclei have possibility to undergo double beta decay. Okay, double beta decay, which means if you have one isotope of A and Z, atomic mass number and mass number, and it will instantaneously decay to AZ plus 2. Okay, it skip one isotope at the center. Okay, so in order to observe this Majorana neutrino, so actually physicists need to investigate their transition rate from here to here. Okay, however, for normal double beta decay, which involves 2 beta, so they obtain some value which is around 10 to power of 3, or about 2 or 3 order of magnitude difference for the normal double beta decay and neutrinoless double beta decay. So due to this confusion, so actually there are some theoretical calculation have undergone. So actually if you look here, the estimation for matrix element of this neutrinoless double beta decay have very large uncertainties. So from 3 to 7. Okay, so this is actually 48, 76, 82, and until 150. So all of this is the nuclei that have very good Q value that is compatible for double beta decay reaction. Okay, as I was saying, most nuclei is probable to decay to double beta decay, but this is the most nuclei that have good Q value. Okay. Okay, so because of this confusion, so APEC, this is Asia Association of Europe, okay, recommend that the computational or highly sophisticated experiment related to investigate this nuclear matrix element is very much uh, encouraged, okay, by all the physics society. So that is why we come to our new proposal to investigate this using ordinary muon capture. So why? Because in double beta decay, actually, if we use this muon irradiation, so we can excite this intermediate nuclei to several excited state, which is around 100 MeV, that is similar to the energy possessed by Majorana neutrino. Okay, so Majorana, the normal neutrino energy is around 3 MeV and so on, but this Majorana neutrino is very, very high, so it's around 100 MeV region, so which is we estimated that muon can able to access this high energy region. Okay, so in this reaction, so actually there are two virtual transition that is expected to observe, which is Fermi and Gamow-Taylor. So this transition is actually come from beta. So every beta decay you have electron and electron neutrino. Okay, so this is the beta transition for Fermi and Gamow-Taylor. Okay, so don't get confused. If you are using electron, you can also observe this visual transition, but only Fermi transition. Okay, the most called allowed transition, but Gamow-Taylor we have semi-allowed. We have some forbidden states. Okay, so what happened to quenching problem? So this quenching problem of a GA, this is axial vector. So this is coming from Gamow-Taylor transition. Okay, so they say that this is the reason why the matrix element for two neutrino and neutrinoless matrix element have so much different. Okay, so they said in this experiment of 76 germanium, so it says that there are actually some indication where the GA is quenching. Okay, the value is different by to 20%. But however, by in this Nature Physics publication 2019, they said that it was around 10% region for this when we are using QA value, the axial vector around 0.9 and 0.75. It estimated around 10% of the Gulat-Primakov experiment hypothesis. So they said there are no quenching. So this is the main problem why we need to use this ordinary muon capture to investigate the matrix element. So due to this quenching problem. Okay, so if you look at the top, so this is actually the transition rate for neutrinoless double beta decay, and this is the matrix element, and this matrix element actually contribute by this GA. Okay, so this GA is coming from this is the transition rate that we observe in this experiment. Okay, so our experimental approach is first we measure the energy of the gamma rays and also the X-rays throughout time. So our experiment usually lasts for 1 month measurement. So we look at the time distribution of the energy. Okay, so let's say we irradiate the muon on the target. So it will excite to around 100 MeV, and then we will be testing this coupling to charge reaction region for the right leg testing of double beta decay, and by using several detectors and also scintillation trigger counter. we can obtain this muon capture rate calculation and other investigate the GA province suppression problem. Okay, so this is one kind of reaction that we obtain using the selenium target. Okay, so here we have time from 0 to around 800 nanosecond. Okay, so the time for muon from 0 to 200 nanosecond. So this was actually the region that we can observe the muonic X-ray cascade. Okay, it comes from the normalization and identification for the target surrounding and itself. Okay, so you can see the region that rounded by green is the muonic X-ray region. And then when goes to the window energy of around 200 to 2000 nanosecond. So actually this is the delayed spectra part. So this indicate the partial muon capture rate. So this actually coming from interaction of muon with the singlet and triplet spin state of the bound nuclei. Okay, so and it was indicated by this structure here. Okay, if you look at this decay scheme, so this was the region for prompt and delay. And the final is when the time is much greater than the muon gamma time. So this is marked as uncorrelated spectra. So this require calibration of detector and some radioisotope identification. Okay, and it follows the yield of short-lived radioisotope during exposure. So this is this region one. Okay, the beta when this decay to the ground state. Okay, so if you are not sure, you can just go back to slide 9, 7, and 10. So this indicate the phenomena that I to explain here. Okay, so this is our latest PSI campaign in 2021. It started from last October to around 15 November, something like that. So we stop. So in this experiment, so we are using 8 germanium detector. So 4 N-type and 4 P-type. So this was, we did not borrow, but we just lend it from our collaborators from PSI, then University of Zurich. Okay, and then we have this trigger control, the CO, C1, C2, and C3. So this is just the trigger counter, just to check either the muon is stopped or not. So because this is the first primary selection to muonic X-ray. Okay, and then we use some DAQ from MIDAS and also online analysis and backup. Okay, sorry. Okay, so in online experiment, so we can separate by timing of 0 to 200 and 200 to 2000. So the prompt and delay spectra can be split like this. And then all the peak will produce this decay spectrum. Okay, from each peak. Okay, so remember, if you have 100 peak, then you need to investigate 100 decay curve, something like that. Okay, so and we also make some calculation using theoretical P and QRPA, and what we can conclude here that the value is almost around 10 to 20% difference. So this is for 1 minus state and 2 plus state and 2 minus state. Okay, so this is actually the outcome from the prompt and delayed measurement that have been observed on beam. However, we also have some continuous uncorrelated gamma ray measurement. So this is by the background radiation. Also, we have two setup. So one is in the experimental hall, online setup, and another is in the offline setup. So the offline setup is rather more simple because we have just detector and also targets. But the online, we have like 8 HPG just extract their number of isotope.
Hi,
So,
Dr. Izyan. Oh, yeah. Okay. I'm sorry just now because your voice suddenly got cut off, but now it's back. So
oh,
sorry to interrupt. Yeah.
okay. So, in this experimental gamma peak, so this is the probability of emission. So, actually, this was calculated from the gamma energy of the each peak. Okay, so we can get this probability. And what we do, so this is our part for Malaysia part. Okay, so we develop one model to investigate this background radiation. So this is for my PhD student. Okay, we compare the one that is produced by model and the one that we calculated from experiment, and we will obtain this some kind of capture distribution. Okay, so actually capture distribution, this value is actually the same with this value. Okay, only this is the illustrated part and that one is more written part. Okay. Okay, so when we compare with experimental is coming from our model, and then the black is coming from PNQRPA. So we will obtain this absolute capture strength. Okay, what absolute capture strength do is actually it was the sum up of 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we sum up all this. This is called partial capture, and the offline analysis is the total capture. Okay, so this is the total capture. So it called absolute capture strength. Okay. Okay, so this is some of my work starting from 2012. So we start with one HPGE detector. So this is a paraffin block. So to block this neutron, because at first in music in 2012, this is beamline is just started to operate. So they have very high abundance of neutron contamination. So we need this paraffin block to block the neutron. Okay, and then in 2014, we repeat experiment in J-Park, Tokai. So now, because we find out that one gamma detector is not enough, so we use two, and then we repeat with three, and we continue to increase the HPG until now we have eight. So actually, this one is much more intense measurement. So this we borrow our mini ball detector from Berlin. So, but this detector does not have the sensitivity that we wanted because it was using NAI scintillation. Okay, so actually NAI scintillation is have low efficiency compared to germanium detector. So in 2021 to this year, so we change back to HPGE detector. So anyhow, here also we have to germanium detector just to confirm the measurement. Okay, so this is a experimental series from 2010 to 2021 and more to come. This is until 2025. So actually, even though if you see that we have some repetitive experiment, so this is because we does not only measure for one physics, but we measure for partial capture, for total capture, for gamma rays and so on. So we wanted to have intensive experiments, so we repeat it again and again. So somehow, actually in our early time, so we focus for beam time around 3 days, but now we need to much longer measurement. So we have enough statistic for the double beta decay, neutrinoless double beta decay. Okay, so this is a part of contribution from our collaborators. So this is everyone. So the Malaysian part is the offline analysis, data taking, and calculation, and also development. Okay, so as a conclusion, so what I can say here that we can say Muon is a very sensitive tools to probe these properties of double beta decay. Because of this experiment have become more mature and we develop more sensitivity measurement. So the unique information that can obtain by this OMC is that its contribution to the theory of double beta decay and astroparticle physics research. So astroparticle physics research is because solar neutrino also have the same energy region around 100 MeV. Okay, so it gives some contribution. And then we hope that in future we have more theorists and also experimentalists from Malaysia to join us in some of our beamline, and we can explore more. Okay, so I think that's all. Okay, thank you.
Okay. Thank you, Dr. Izyan. Thank you very much for your interesting sharing about your research and also about the theory of muon capture. So I believe now let's proceed to the Q&A session. Is everybody okay with that? I'd like to. Oh, there are a lot of responses, I see. Okay, a lot of emoji responses. Uh, yeah. Okay, Hong Jian will be sharing. Okay. All right, Dr. Izyan. So we have a few questions from the audience from the floor. So I think we'll start from left to right. Okay, I'll read. So hi, Dr. Izyan. For students who want to further pursue their studies in muon capture, may I know what are the prerequisites one must acquire during his or her undergraduate studies in order to pursue this field?
Okay, so if I will say in terms of what my requirement for during my master, because master and PhD also I do somewhere else, and the expectation of our collaborators. So actually, they require you to become to be hardworking. Okay,
Okay.
so first that is Japanese standard. They want you
Okay,
to be
Japanese style.
so
Okay.
actually, if you have the basic of nuclear physics, elementary particle, nuclear instrumentation, programming, and that is the bonus for you. Okay, so actually this is two different background. For Japanese, they insist that you know this basic standard, but for European, so actually some of the electronics. So actually, we need to know the electron, how to signal processing this reaction. But for European, actually, they sub this project to engineering part, so they don't have to do
Mhm.
half of it. They just concentrate on the physics. So that is why it depends. If you
Mhm.
are trying to pursue in Japan, then you need to be more hardworking. If you for European, then actually you need to hardworking enough so that you know the theoretical part, but you need to explain to this engineer to how you want this process to be happening.
Okay, okay. That's interesting. So I wonder if quantum field theory is needed in this field. I suppose it is, right? If
Yes.
we need to have a very basic quantum field theory understanding.
Yes.
Okay. All right. Let's proceed to the next one. So the next one is do you have any recommendations? Oh, I think this is already answered, right? But anyway, I'll ask again. Do you have any recommendations, like any institutes for us if one wants to study specifically in this field?
Okay. So
Yeah.
actually, there are around 4 to 5 beyond facilities around the world. Okay, two of them is in Japan. So one is in Osaka University, and another one in J-Park. Uh, these two actually you can directly from go to Osaka University, or actually there are some collaborators for this university. So actually,
Mhm.
anywhere also you can contribute to muon capture. Only if you plan to become the accelerator physicist, so I would recommend you to go to these facilities. And another one is PSI, the one that I go to Paul Schroer Institute,
Awesome.
and we have RICAN RAL in UK, and another one is in Canada, Triumph. Okay, the only
Okay.
difference is that for Osaka and PSI and Triumph, so they they use DC, direct current type, which is continuous muon beam. But for recant, they use continuous muon beam, but usually they are using for material science only, not nuclear physics. So no high energy. But for JPAC, it was a pulse beam structure.
Mm,
So there's
okay.
some
There's
difference.
there are some difference. I see, I see. Okay. Okay, that's interesting. So, for those who really want to do muon physics, please take note. Yeah. Okay, and now the third question. Doctor, are we okay? So what it's trying to say is it possible to recover new elementary particles in our universe? Mm, I'm not
Okay,
sure what the question is about, but anyway, yeah.
elementary particle in our Okay, so actually the aim for elementary particles, so actually if not sure USM is the student attending here have attend elementary particle class?
I don't think we have elementary particle classes here, but we do have nuclear and I'm sorry, what was that again? I think we have a nuclear physics class, but we don't have a elementary particle physics class.
I
Yeah.
see. Okay, so at present, uh, physics within standard model is the one that I showed you before, the standard model. So actually there are physics beyond standard model, which is known as grand unified theory. Okay, so grand
Mhm.
unified theory actually they postulated that some uh, the requirement for electroweak theory. So the how the energy is coming from electromagnetic interaction and weak interaction is combined to each other. Okay, so there are some specific energies to shared energies to observe these two kind of reaction. But actually, there are another physics more beyond. This is a super grand unified theory. So where all strong interaction, weak interaction, and electromagnetic interaction actually merge to one energy. So at here, so actually they postulated there are some. Now we said that we have neutrino, the one that neutral particle. Then they have this neutralino, photino, gluino, and momo at the back. So that is the super grand unified theory.
Okay. Okay, okay. Super grand unified theory. Okay. I'm gonna let that sink in my mind for a moment. Okay. Anyway, okay, so now let's proceed to the fourth question. Doctor, is there direct experimental confirmation of the existence of quarks?
Okay. Actually, yes, for the quark, so actually not muon. There are some actually quark discovery experiment from 2000, around 2000 and so on.
Mhm.
So it was done in CERN and also other very high energy. So because in our experiment we choose until 50 MeV, but for in CERN they are using around 3.6 tera electrovolt.
There you
So that is a very good energy to observe this quark. Okay, so actually this one they are using the ion and positron interaction to observe the new quark. By the way, if you are interested in the existence of quarks, actually they are open for summer school at CERN from September, but now it's
go.
open for application. So if you are interested, you can join.
Yeah. Okay, yeah. I've heard of that too. I saw many people sharing around. Yeah, the summer school. Okay. All right. So now we have one more. Actually two more in the Padlet. All right. So it says that may I know what type of programming, it could be C++, C, Python, or Maple, that you are using or you tend to use when you are handling the data and also the simulation.
Okay. So for now, we are using C++ and Python for now. So I'm not sure anything else because actually there are different analyses for the online and also offline. So for our case, we concentrate more on C++ and Python.
Okay. Uh, i- Dr. Izyan, is any of your colleagues using Fortran? Because I've heard that people using Fortran to do simulations and also data massaging. Is that true?
Actually, Fortran is mostly used for theoretical studies, the model, the PNQRP and so on. But
Mm-hmm.
anyhow, I think from 2020 they started to migrate Python.
Python.
Okay. But I'm
Fortran
not
is
sure.
kind of a old.
Yes,
I've heard they say Fortran is kind of a very ancient language.
yes.
Yeah, okay. Okay, thank you. One more. Okay, we have one more here. It says, Dr. Izyan, could you describe a bit about the newly found Muon G-2 experiment? Is it giving an impact on your research?
Actually, the Muon G-2 experiment is related to determining the muon spin, which is at first we said that muon is in the same group with electron, which is electron is fermions. So they
Mhm.
said that in order for muon to have this same spin, it need to fulfill the quantum electrodynamic studies. So they are using this muon G-2, but however, we did not have any impact to this research because actually if you want to concentrate everything so it will be more because this as I was saying this muon G-2 involving the polarized negative muon, the very
Mhm.
low energy, so we did not concentrate on that for at this.
Okay. All right. Oh yeah, Muon G-2 is done at Fermi Lab, if I'm not mistaken.
Yes,
There's the G-2 experiment. Yeah. Okay. All right. Seems like these are the questions from the pet. Oh, there's one more again. Okay. Just right before we end, there's one more again. May I know what is the significance of muon capture? What particle physics phenomena regarding muon capture as I as I have little knowledge about it?
what is the significance? Okay.
Probably is more on the particle physics field.
Yes, for this, actually, in the muon capture process for particle physics, we have this three rare transition, which is more muon to electron, and also with no gamma photon emission. And also we have this muon to three electron. So actually, this contribute to the charge lepton flavor violation. Okay, so muon have lepton number.
Mhm.
Okay, so when muon transfers decay into electron, so actually without existence of muon neutrino, so actually the lepton number of muon is violating. Okay, so before left hand side is one muon, another one is no muon. So that is charge lepton flavor violation. So actually there are two experiments focusing on this experiment, which is the syndrome at Triumph, okay, Canada, and another one is COMET at coherent muon electron transition. This one is in Tokai. Okay, so both experiment actually they syndrome have started its physics experiment, but COMET maybe they will start somewhere next year or next 2 years.
Okay. So, all right, since these are the questions from the Padlet, Dr. Izan, I personally have a few questions. So earlier you said about the muon capture can be used in medical applications, and if I'm not mistaken, medical applications and also radioactive waste the how do you call it? It's not decomposition, but disposal. Is it about the
Yes.
disposal of nuclear waste, right? So I was wondering if it is now being used extensively or is still under research so that it could be used in the future.
Actually, it's still under research. So because the thing
Mm-hmm.
is that in order to produce some isotope, it is simple, but the thing coming up is how to extract this kind of isotope. So they found a way to produce, but to extract they need some facilities to keep this radioisotope in at the same at stable
Okay.
place.
Okay. All right. Seems interesting. So it seems like we have a few more years to see, and to get better results so that it improves its efficiency, is it?
Yes, correct. That's correct.
All right, all right. Okay. I think I have one last question. Uh, is somebody turning on the mic? Oh no. Okay, I think I have one last question, which is about the physics beyond the standard model for muon capture. I was thinking if, first of all, if the research is now already ongoing or it's just on the starting point. It's just going to start or it is already undergo. It's already underwent.
So it's actually started in the early 2000 maybe.
Oh,
It
okay. Oh,
started,
that's very fun.
but because you know earlier 2000 it is starting of a economic crisis, so we don't have enough money, and then something and go, and then the progress for theoretical is very much dependent to experimentalists, but experimentalists cannot find. If you look at my experimental series, so actually we plan to have beam time every year so that we can progress much faster, so that we can give some feedback to these theoretical physicists and so on.
Okay, okay. That that's very interesting. We are very, very aware. I think we are very willing to wait and see since there are many years to go. Okay. So I think that is the end for the Q&A session. Everyone, thank you for once again thanks everyone for submitting their questions and also being quite active. So before we go, could we have a photo session? I think let's have a photo session. So to commemorate this event. And yeah, uh, just as a note for USM students, please turn on your camera at least for this photo session because we'll be judging on how you perform, which is if you turn on your camera, then you only get the my safety points. So yeah, this is a way. So please turn on. Thank you very much. I'll give you around 2 minutes for most of you to turn on your camera. So please get ready. Um, you might wanna go and have a simple makeup, or I don't know. What anything you can do on your face just to look better, you can go and do it. All right, let's see. So, by the way, Dr. Izan, where are you right now? Are you at UTM or you are at uh, you're attached to postdoc a different institute?
Currently, I'm still in UTM.
Oh, you are still in UTM. Okay, this is interesting. It's pity because it's the pandemic, or else we can make a visit or something. We can bring students over probably.
Anyhow,
Yeah.
we will soon start try to give some feedback about our particle physics school for Malaysian. So we hope
Mm-hmm.
that we might have some time to visit USM for this event. So
Okay.
that we can go to all universities in Malaysia to introduce particle physics and how we are using this experiment and how Malaysia
Oh, okay.
as a particle physics community and so on.
Okay, that's interesting. I'm eagerly waiting for that. I'm hoping to see that maybe in this year, probably. No, I think it'll be next year because this year doesn't seem very good yet.
Correct.
Okay, seems like how many of them have turned on the camera? Not much, not much. How many slides do we have here? Oh, there are a lot of participants. How many participants do we have today? We have 92. That's kind of a lot. 92 of them coming in. Hmm. All right. Um, how about the rest? The rest are not, not responding. So, Dr. Izan, is it okay if you would like to wait for around about half a minute?
Yeah.
Not 1 minute. All right. All right. I think it's taking kind of long, so I think we'll just cut short. Give you 10 more seconds to turn on your camera, then we'll take the pictures ready. All right. I think, Dini, I think you can start to take the pictures. All right, everyone, please bring out your best expression you can have. Bring out your best smile, you know. All right, Dini, would you mind to turn on your mic?
Hello.
Okay. All right, we can hear you.
Okay. 1, 2.
All right, for the Dini, maybe the first one you've taken for the second one, for the second interface.
So 1, 2.
Okay, for the third one.
Dah tak ada yang buka.
Oh, still haven't opened. I think it's okay. You just keep on taking. Yeah, it's fine.
2, 3.
Okay. All right.
Very good. Done.
Okay, Dini, you've done, right? Okay. Uh, all right. So thank you everyone for turning on your camera. It's been an very fun to that guys turn on your camera and we can take pictures on it. All right. Yeah, before you go, everyone, Jian, how would you like to, can you share the attendance, yeah, in the chat box? And yeah, Hong Jian will share the QR link. So everyone, you can scan the QR code for your attendance and also the feedback, or you can access the chat box. So there is a Google Doc, you can go in and fill in for your attendance and also provide us some feedback. So yeah, this meeting will end in 5 minutes. So thank you once again. Thank you, Dr. Izyan, for joining. It's been an honor to have you here. And enjoy the rest. To everyone, enjoy the rest of your weekend. And see you around. Thank you, Dr. Izyan, once again. Thank you.
Okay, thank you everyone. Thank you.
Thank you.
Okay,
Okay,
bye.
thank you. Bye. Just to let you all know that this meeting will end in about 3:37. Thanks everyone for joining once again. We hope to see you in the next event and enjoy the rest of the afternoon and the evening.